And we are going to watch a little video. This is Mr. Veritasium before he was Mr. Veritasium. It was way back in the day. Okay, here we go. Oh, and I should have closed captions. There we go. And voltage is what we're going to be looking at today. So that first part was just review. Hopefully it just helped remind you of all the things you've learned so far. And now on to the next bit. Okay. So that gives you a little idea. Okay, we're not doing that. We've been there and done that. All right. So here we have on page 72, this will wake up, we're talking about voltage, which the symbol is capital V. And it is known as the potential difference. It is the difference in electrical potential energy. The difference in electrical potential energy. And because we often use the term potential energy, we can give it the abbreviation PE. Okay, potential energy. Do you guys know what we mean when we talk about potential energy? Potential energy is stored energy. When you release stored energy, it is transformed into a different form of energy, and that comes out as some sort of work. Okay, so when the electrons move from one side of the battery to the other side of the battery, they can do work in a light bulb, giving off light. They can do work in a motor, driving the motor. Okay. So in our lake analogy, here's the lake where there is no current flowing. The potential energy on the left is the same as the potential energy on the right. So if we were taking a look at gravitational potential energy, Jerry, come sit over here, please. Beside Ella. Her partner's away today. Then you're right in front of me, just right here. Thank you. Bring your book. Okie dokie. So potential energy is the same on both sides. It's like if you had this book and I put a pencil on one side, it doesn't roll because right now the potential energy on this side, gravitational potential energy, is same as I'm not very good at holding it straight, is the same as the gravitational potential energy on the other side. But if I tilt it, it's going to go from an area of high potential to an area of low potential. I have so many open seats. So if you would like to talk about something other than science right now, you can move to one of the other open seats in the class today. We're missing a lot of people, so lots of options. If we lift that lake, we have a high potential energy. And down at the bottom, we have a low potential energy. And what we have here is between these two, we have a difference in potential energy. You think I can't hear you, but I hear everything. So we have our high potential energy, we have our low potential energy. And is that difference in potential energy that causes the current to flow. Everything always wants to be at the lowest possible potential energy. Things up high are unstable. Things that are at a lower potential energy are stable. And nature always wants to go from less stable to more stable. So here is our battery. And it is as though this battery takes the bucket of electrons, right? And it lifts it all the way to it's like a little elevator in there, and it lifts it to the top of the battery, the negative end of the battery. And once it's up at the top, it has, up at the top here, each bucket of electrons contains 1 joule. Do you remember that word joule? What is a joule? Anyone remember? It is the unit of energy. The joule is a unit of energy. And it is abbreviated with the letter capital J. Okay? Joule, capital J. Each bucket of electrons contains 1 joule of potential energy. And that is at the top of the battery, at the negative end of the battery. Okay? So that's where each bucket of electrons contains 1 joule of potential energy. As the electrons get down to the bottom, all the way along here, maybe I should do that in a different color, all the way along here, down at the bottom, each bucket of electrons contains 0 joules of potential energy. And sometimes people get a little messed up because they think, well, if the electrons over here contain 0 joules of potential energy, then why don't they just stop moving, right? Because they're at the lowest they can be. But what happens is each bucket of electrons pushes the electrons ahead of it. Yeah? The battery pushes the electrons to the top. As these electrons go down, they push the electrons in front of them, and there's no real gaps. This shows lots of gaps in between the buckets, but if you can imagine that there were buckets all along the way, if you have things flowing downhill, it's like you've got, I don't know, like if you had what's the word I'm looking for? A roller coaster that had all the cars, but it was attached all the way around. If you move one of the cars, all the cars are going to move because they push the cars in front of them. Okay? So the greater the difference in height for a river, if we have a bigger difference in potential energy, we'll have a bigger current. So in a river, the greater the difference in height, so if you started off at the top of the mountain and your river finishes at the end of the mountain, it's a very steep mountain, you're going to have a very fast current. For electrical potential energy, the bigger the difference in potential energy, the bigger the current will be. So, definitions that you need to know. You need to know that voltage is electrical potential difference which is the same as the electrical potential energy. And what does potential energy have the potential to do? It has the potential to do work. Potential energy is the potential to do work. And what could work be? Work could be moving a motor. Work could be lighting a light bulb. Work could be, can you guys think of something else a battery could power? You guys work with stuff all the time that has batteries in it. Phone, yeah, it could run your phone. Okay, anything that uses a battery, a remote control, okay, it could allow those signals to come out. That would be the work, okay? Work your remote control. So now voltage isn't just potential energy. It is the potential energy contained in one bucket of electrons, okay? Voltage is the electrical potential energy contained in one bucket of electrons. So in other words, it is the joules contained in 1 coulomb of charge. The joules of energy in 1 coulomb of charge. So voltage is joules per coulomb. We could also write it as this, joules per coulomb. And remember, the symbol for joules is J. So we could write it as J over capital C. So those of you who were doing unit cancellation yesterday, you'll notice you had 1 unit on top of a second unit, and that'll allow you to do some cancellation. We'll be able to do that with volts if we write them as joules per coulomb as well. Okay. Now, a joule per coulomb is also known as a volt. Just like an amp is a coulomb per second, a volt is a joule per coulomb. And the symbol for volt is V. So voltage, this one is actually pretty straightforward. Voltage is the quantity and volts are the units. And the abbreviation for both of these is capital V. So that's really straightforward, okay? The unit is V, the quantity is V. So this is just a little illustration. If you just look at 1 coulomb of charge, 1 bucket of electrons, So this is on our next page. Okay, so that was page 73. Now we're on page 74. And we have this little picture here with the light bulb. Okay, so if you're not on the page with the light bulb, you want the one with the light bulb. And at the bottom of the page, you can write 74. So we have one bucket of electrons, and it contains 1.5 joules of energy. So that's 1 coulomb of charge containing 1.5 joules of energy. What's going to happen to that energy? Well, as it goes down the wire, whoa, what happened? Bye-bye. Okay. As it goes down the wire, that coulomb is actually going to pass up into the filament of the light bulb and down back into the wire again. As it passes through the light bulb, it's going to give off energy. So the bulb gives off energy. What type of energy does the bulb give off? Have a think about that. Talk with your partner about that. What? I think it's mine. Yeah. Okay. Yeah. Yes. Perfect. Good. No worries. So this bulb gives off energy. What type of energy is it giving off? It's giving off light and heat. Now, if this little bucket of electrons started out with 1.5 joules of energy, how much light and heat energy comes off the light bulb? How much light and heat energy? Same amount. 1.5 joules of heat and light come off of that light bulb. And by the time we get to the bottom, we end up with that 1 coulomb of charge. That one bucket of electrons has no energy left. So no matter what you have in that circuit, no matter whether you have a light bulb or a motor or a speaker or a remote control or whatever, you're always going to use up all the energy. Okay? It always gets back down to 0 by the time it gets back to the positive terminal. Okay? What do we call this 1.5 joules per coulomb? We would call that 1.5 what? 1.5 volts. Down at the bottom, we have 0 joules per coulomb, and that is 0 volts. And are we just about done? Is that why we're all packing up? Yeah, we're just about done. I will see you tomorrow. There's no homework. We'll pick up where we left off. Yes. Okay. Okay. Have fun. Okay. Thank you for letting me know.
The homework.
Hi. Yes. Perfect. Thank you. Thank you.
Wait, I have a few questions.
Yes.
So here on the solve, do I
Yeah.
need to show my work?
No.
Or can I
If you can just do it in your head, that's fine. Yeah.
I
Hi.
also want
Okay.
the week.
You are going away?
As well.
Oh, nice. Enjoy. Aren't you lucky?
And,
Hi, Kate.
I've got a question about that.
Yes.
And so you told me
Uh-huh.
that all the energies
Uh-huh.
are lost
Yes.
when the electrons go through.
Yeah.
But in reality, like
Uh-huh.
we connect two light bulbs linearly and connect to the battery.
Yeah.
And the first light bulb doesn't like exhaust all the energy, but like half of them goes to the second one, right?
Okay.
How does it work?
Okay. This drove me nuts for a long time. It took me so long to figure out what the hell was going on. I'm like, what? Why is it not dropping all its energy in the first one? So what happens is anything that uses up energy has a certain resistance to flow. Okay. And you can think of resistance as being like if you had marbles flowing down here and you had pegs all along here,
Yeah.
it would stop them from flowing as quickly. Now, the more pegs you have, the more resistance there is, and the more it slows it down. Okay? So the more pegs you have, every time we're just going to think about heat energy, okay? So every time it hits a peg, it's giving off heat energy because it's causing a bump and everything's vibrating, right? So heat energy comes off. But if you have two sets of pegs, like let's assume we have a set of pegs here, and then we have no pegs, and then we have another set of pegs here, right? So we got one here, nothing here, and then one here. These guys are going to be slowed down by this set of pegs. So they're also slowing down these guys, right? Because there
Because
is
they're
no
all, like,
such
all
thing in a
connected.
break
Yeah.
of electrons, right? Like there's always electrons everywhere, right? So if this is slowing down the flow of this, then not as much heat is being lost here because they're moving more slowly. Yeah? Did that
Yes.
make sense?
I'll think about it again.
Think about
Yes.
it, and feel free to talk to me again about it because it took me a long time. I kept thinking I got it, and then I'm like, oh no, didn't get it. Think I got it? No, I didn't get it. So yeah, if you get it in grade 9, you're brilliant. So there you go. Yeah,
Thank you.
yeah, excellent
Wait,
question. Hi.
Here, since there's two sig figs,
Yes.
and the answer is 125,
Yeah.
should I just leave it at 125?
If
the
you want the
English?
sig figs, you would round it to 130
130?
Yeah.
Okay.
because that would
Or
have two sig figs.
120 doesn't make a difference.
Yes, you should round up if you're at the
Okay.
5. Yeah.
Okay.
Okay.
And oh yeah, can I put the solve and the
Oh yeah, you
substitute
can do
together?
solve and substitute can all go together. That
Okay.
makes the most sense. Yeah, absolutely.